It's question show time. Your questions, my answers, as always, wherever you are, across my channel. If a question pops into your brain, just write it down. I'll gather them up and I'll answer them here. And we haven't had a lot of great questions. I beg you, if you have good questions, just have this be an instinct. You're like, oh, that's interesting. I was reading this news story. I was watching this TV show. I was watching this science fiction. I want Fraser to tell me the answer. Come back to my channel, write down your question, and I will try to answer them here. Lots more guest answerers coming up, lots of live stream stuff. So hopefully I can still continue to be your one-stop shop for space answers. All right, let's get into this week's questions. Best beans. Question regarding the Fermi Paradox. Is Cixin Liu's interpretation where the universe is like a dark forest with civilizations forced to hide and annihilate each other based on chains of suspicion sensible? Thanks. All right, I don't want to spoil the trilogy of the three-body problem trilogy too much. The dark forest trilogy? Anyway, first one is the three-body problem. Second one is the dark forest. Oh, I forget the third one. They're fantastic. They are amazing, incredible books. I really enjoy them. The first one's a bit of a slog. The second one is like really kind of expands your mind and it's quite exciting as sort of you don't know what's going to happen next. And then the third one just blows your mind. Like it deals with concepts that will just leave you stunned. So if you can, get your hands on a copy and read the trilogy. They're fabulous. Now, in the books, the idea is, the dark forest is that civilizations across the Milky Way keep their mouths shut, because if anyone out there finds out that you're there, they'll come and deal with you. You can imagine what that means. And so civilizations try to hide and try to keep themselves secret. It's a cool idea for a sci-fi story, but it doesn't really hold water for me as an explanation for the Fermi Paradox, because there's no real way to hide your civilization in its entirety. Planet Earth has been generating the kinds of biosignatures, enormous amounts of atmosphere, oxygen, ozone, methane, phosphine, all kinds of products are in our atmosphere that would be detectable and have been for 500 million years. So before we got to the point that we were technologically sophisticated enough to know that we should try to hide from the rest of the Milky Way has already known that we're here. They've watched us move through every single cycle. They watched when the oxygen rose in our atmosphere. They watched when the air pollution started to show up in our atmosphere from us being an industrial civilization. They watched as chlorofluorocarbons started to go into our atmosphere, showing that we were getting to a high level of technology. They listened to our radio signals with their enormous solar system-wide radio telescopes. So the aliens know we're here. And as we build more and more powerful tools to find the aliens, we're going to know they're there as well. So you kind of can't hide. There would have been no chance to really, the moment you realize that you probably should hide, it's too late to hide and everybody knows that you're already there. So it's weird because we have definitely been broadcasting our existence to the entire Milky Way for 500 million years. Thanks, oxygen. Thanks, phytoplankton. And the aliens haven't shown up to wipe us off the planet yet. So that's weird. So no, I don't find the dark forest theory that compelling, but it is one of my favorite sci-fi series, bar none. Read it immediately. Hurry. Paul Cockerill. Hi, I have a question. How many grains of sand are there in interstellar space, and how much of a hazard and a barrier are they to interstellar travel, say at 20% the speed of light? See, I'm so hard up for questions, I took on questions that required me to do a bunch of research and calculations. This is how desperate I have become. So how much interstellar dust is there? There are approximately 1,000 grains of interstellar dust in every cubic kilometer of interstellar space. And that sounds like a lot. Maybe it doesn't sound like a lot. Cubic kilometer is a very large area, and a piece of interstellar dust, 1,000 pieces scattered across that entire distance is very little. They range in size from about 100 femtograms to about 100 milligrams. So 100 milligrams is, a tenth of a gram. That's starting to get to a pretty serious chunk of interstellar dust. And yeah, if you're going 20% the speed of light, then they're going to hit with 800 times the force of a bullet. In other words, if you have a small spacecraft and you hit one of these going 20% the speed of light, your small spacecraft is destroyed. If you've got a larger spacecraft, maybe they punch a hole right through your spacecraft and don't cause a lot of damage, or maybe they do take out important parts of your spacecraft. And so if you're going to build something small, you're just going to expect that a huge percentage of your spacecraft are just going to get destroyed as they hit pieces of interstellar dust. If you've got a big spacecraft, then you're going to try to figure out some way. You've only got one of them. You're going to need to figure out some way to ablate the damage that's coming at you. And so there's lots of good ideas. Put armor in front of your spaceship. Use ice so that it absorbs a lot of the damage that's coming. So definitely, as we attempt to come up with ways to make spacecraft go 20% the speed of light, interstellar dust, just tiny grains of sand in space, become a pretty big problem. Jim C. If we were to launch a Voyager-type mission today, how long would it take to reach where the Voyagers are today? Is the time it would take more of a question of technology, or even with a more advanced mission? Is it more about the speeds that gravity assists and such can provide? So we're now, 30 plus years after the Voyagers were launched? 40 years? A long time. The Voyagers have been going. They have gone all the way through the outer planets of the solar system, past the orbit of Pluto, and they are well on their way into the Kuiper Belt. There's the Pioneers, which have done sort of the same thing, and then of course there's New Horizons, which is sort of taking its own high-speed journey out of the solar system. The fastest spacecraft is actually the Voyagers, and a big part of it is because they got all of those gravity assists. Voyagers got a gravity assist at both Saturn and Jupiter, and then Voyager 2 went on to get a gravity assist at Uranus and Neptune as well. And so really it comes down to those gravity assists that gave those spacecraft to the high speed. The basic technology that we have today to launch spacecraft is roughly the same that they used back when the Voyagers were launched, back in the 70s. You launch on a very large chemical rocket and do gravitational assists to build up your velocity. A Atlas rocket today is kind of the same rocket as an Atlas rocket was back in the 1970s. Now, there are much bigger spacecraft that have been proposed. There's of course the SLS, there's Starship, and yeah, if you just took a teeny tiny spacecraft and you put it on top of a Starship and you launch it as fast as you could possibly go, you could cut down some of the flight times, but not a lot. You could turn a 10-year journey into a 6-year journey, but you're not going to turn it into a 6-month journey. But there are a bunch of other technologies that have been thought of. There's of course ion drives, which are slow and steady and build up to enormous velocities over long periods. You hook up a nuclear reactor to an ion drive and you can power that thing for a long time and build tremendous velocities. There's ideas of nuclear fission rockets, which could go faster. There's some ideas for some nuclear fusion rockets, which could go very quickly. So until some of these new technologies are tried and tested, flight times out into the outer solar system are not really going to improve beyond the Voyager flight times. Vengeful Sorrow. So it's theorized that black holes will evaporate over long periods of time due to Hawking radiation, but is that negated by the energy falling into them with all the light shining from stars in a galaxy? In other words, will the evaporation of black holes be put off until the universe is less dense with energy? So this idea of black holes evaporating, we've done whole videos about this and lots of other people have as well, so I won't go into all the details, but the gist is that over time, black holes, depending on their mass, will release photons. And in fact, the more massive the black hole is, the more slowly it will release its energy. And so the most massive black holes will last the longest, and the smallest black holes will actually evaporate the quickest. In fact, when a black hole is finally about to completely disappear, it's super white hot, putting out gamma radiation. But when a black hole is really big, it's occasionally putting out one photon. Oh, I got a leaf there. One photon every few, millions of years. I don't know the exact number. So you're exactly right that in our current universe, there are photons coming from the cosmic microwave background radiation of 2.7 Kelvin, and they're hitting everything. And so really, until the background temperature of the universe gets so cold that very few of those photons are hitting the black hole, evaporation won't even begin. We've got to wait until really the background temperature of the universe is almost indistinguishable from absolute zero. And only then will it be cool enough and few enough photons falling into black holes that they're able to give off more mass than they're accumulating from the universe. Russia Gator. Fascinating stuff. Answered a lot of questions I've had about abiogenesis. Something I've been wondering about a lot lately. Namely, why isn't abiogenesis constantly happening around the planet every day? Abiogenesis is this idea, this question of how did you get from non-life to life? How do we go from just a soup of chemicals, some energy in a pond somewhere, maybe a lightning strike or two, to life forms that could replicate and turn into the vast diversity of life forms that we have on Earth? And we don't know the answer to that. Anybody that tells you the answer to that is lying. They don't know. They're making stuff up. Someone told them a thing. They don't know how it happened. But at this point, we kind of know the overall steps that had to happen. You had to have really simple chemicals like methane, hydrocarbons like methane. They had to come together. We see methane in various places around the solar system. Titan has all kinds of hydrocarbons on its surface. And then you had to go to more complicated amino acids and sugars. And in fact, we see those across the solar system and out in space. So we know that those can happen. And those had to turn into kind of larger molecules that interacted with each other. And then at some point, and this is sort of the magic step that we don't know how it happened yet, that they started to interact with each other in some kind of environment. And then at some point they got some kind of membrane around them that protected them from the outer environment. And so you had sort of the mechanism inside different from the mechanism outside. And then eventually you got to this whole process of variation and natural selection and just sort of reproduction over time. And so we don't know how you got that intermediate step yet. And biologists are trying to work it out, and who knows? Somebody might put the right groups of chemicals together, and what do you know? You got life, or you got the basics of life. It's when you think about it, it's like like when you load the operating system on your computer. Like when you first start up your computer, it doesn't have to create the entire operating system. It just has to do the bootloader. Whatever's the bare minimum to make your computer get to the next step. That's all that has to be present. And same thing with life. Whatever that first abiogenesis event was, it just had to be the bare minimum to get to that next step. So the question you're asking is, why isn't this happening all the time? And so one possibility is it's only happened once in the history of Earth. And we happen to be the result of that one-time event. The other possibility is that it happened a bunch of times, but it's still fairly rare. And this life form was the life form, and I don't mean just me, but like DNA-based life, was the one that was successful and outcompeted in every environment. And every time an abiogenesis event, some feeble creature begins trying to replicate, a hungry tardigrade eats it up. And so you've got this sort of, there's no place left on Earth because all of our life forms have taken over. And then the other idea is that it has happened multiple times, and it turns out that all of those life forms are still hiding, that we don't recognize them. And we did a whole episode about this idea of a shadow biosphere, that there could be other life forms sharing this planet with us, living in places that our life doesn't want and is doing just fine, and we just haven't discovered it yet. So there's a lot of unknowns. We just don't know the answers to a lot of those questions. Connor Paller. How do you determine the habitable zone of a sun that is different from ours? I mean, there are so many different kinds of stars out there. How could they possibly know when a planet is in the habitable zone when it's that far away? The habitable zone is actually a very simple calculation. It's really just what is the distance from a star where planets around that star could have liquid water on their surface. So if you have a star like our sun and you have a planet orbiting at the distance of Mercury, then any water on the surface of that planet will be boiled away and blasted off into space by the star. But if you get out to the distance of, say, Venus and Earth and Mars in our solar system, liquid water could be present on the surface of any of those planets depending on the atmosphere, essentially. If the atmosphere is really good, then it will be supporting liquid water on the surface. If the atmosphere is really bad, like on Mars or on Venus, then it doesn't. And so we end up with a place like Earth, which does have liquid water. So how do you calculate that out there in the universe? And so astronomers, what they do is they just take the luminosity of the star, how much light is the star putting out, how much radiation, and then they calculate that habitable zone. And so if it's a red dwarf star, you know, one of those really small stars, then the habitable zone is really close to the star, and it's very quick. Like you've got too hot, habitable zone, too cold, all the way out. But if you've got like a really big star, a Betelgeuse or a Rigel, then you're going to have a very large habitable zone where you could have planets. Of course, those stars die really quickly, so you wouldn't want to live around them. But anyway, and so every star will have its own habitable zone that can be calculated, and that's where you look for planets. More questions in a second, but first I'd like to thank Zachary Fluke, Robert Madsen, Ryan Schluter, Tom Litzinger, Dan Gottfried, Brad Kilshaw, and the rest of our 890 patrons for their generous support. Want our videos early with no ads? Join our community at patreon.com/universetoday. Gregory McKinley. Question: how close could two star systems be without each star's gravity interfering with the stable planetary orbits of the other star system, and how long would it take for an alien civilization to travel between the two systems with current or projected technology? I'm wondering if it would be possible for each system to have an alien civilization where they could become friends or enemies. So there's two kinds of binary systems that could support habitable planets around them. And so the one type is called an S-type, or a single type. And what you've got is you've got essentially a star, you've got a bunch of planets orbiting around that star, and then you've got another star that the two stars are orbiting around each other. So imagine you've got kind of two solar systems that are orbiting around each other. And so you've got one habitable star planet orbiting one star, and then there's another star system, there's habitable planets around that other star system. And so the question is, how close can those stars be before you've got some kind of danger? And the ratio is 1 to 5. So what it means is that if the Earth is 1 astronomical unit away from the sun, then that other star can be 5 astronomical units from the sun, and it won't perturb the orbits. Any planets around those two stars will be stable. And 5 astronomical units is not very far. That's like the distance to Jupiter. So if you had one star and then another star at the distance of Saturn, say, and you could have habitable planets around both of them, and the whole system would be stable. And you could send spacecraft from one star system to the other. The other version of this is where you've got two stars that are orbiting around each other, and then you've got planets orbiting around those stars. And in that situation, you need to have your planets like a little farther away, but they can still be stable around both of those stars. As long as they, as long as they're far enough away from the stars, then they'll be stable. But I think the one that you're thinking about is the one where you've got the two stars orbiting around each other and both have a star system around them, and then people can go from star to star. Rick Robinson. I wonder if L4 and L5 would hold interesting small rocks from the beginning of the solar system. Sounds like areas for exploration. Might even find a few derelict alien ships. So the L4 and the L5 point are these stable points that orbit around or in the same orbit as any planet. So Earth has an L4 and L5 point ahead and behind it in orbit. Jupiter has L4, L5 points ahead of it and behind it in orbit. Saturn, etc. And the L4 and L5 are gravitationally stable points. In other words, if a thing is in the L4 point, it will be able to remain there pretty much forever, while the other Lagrange points are unstable and stuff rolls out of them and can't remain there for very long without some kind of assistance. And so when you look at the L4, L5 point, though, it's not like the bottom of a valley where things roll down and end up at the bottom of that valley. It's more like it's a point where things are orbiting. And so you can actually have a very large area where things are orbiting around and they're in the L4, L5 point, but they're still millions of kilometers away from each other. So it's not really like a place you go to one spot, like the garbage gyre in the Pacific Ocean. Go, okay, there's all the junk right there. You would be getting close to them, and you'd be getting a lot of flyby opportunities if you hung out at an L4 point, but you wouldn't be able to just sort of go to the very bottom of the L4 point and then just scoop up derelict spacecraft and pebbles and stuff from the beginning of the solar system. So it's not the right place. Sean G. Hey Fraser, question. Could we detect gravitational waves emitted outside particle horizon? The early universe was blocking lights from traveling, but not gravitational waves. There's an area outside the particle horizon, but still within the event horizon. If yes, where were they from? A universe that has no causality with our Big Bang by then? Thanks. The farthest that we can see in all directions is the cosmic microwave background radiation. This was like the moment the entire universe had cooled down to the point that light could escape. It was roughly the temperature of a red star. So if you could go back to the early universe, the moment the light could escape, everywhere you looked around would have just looked like this dull red color that was as hot as a star. Like, you wouldn't want to be there. And then quickly it cooled down to, now it's at 2.7 Kelvin, so it's very cold. But that's not the beginning of the universe. That's about 370,000 years after the Big Bang itself. And so before that point, the universe was hotter and hotter and hotter and hotter, and so hot it was like the interior of a star. But there was still a universe. But we just can't probe it using light because the light was trapped inside the star until it cooled down and then we could see it. I know it's a mind bender. But one thing that was happening before then was gravitational waves. And so in theory, with a really powerful gravitational wave observatory, we should be able to see the primordial gravitational waves, the gravitational waves that were released during the Big Bang, after the Big Bang, all of the times up until the cosmic microwave background radiation was released, and then we could use light as well. But we could even still use gravitational waves to see the first giant stars crashing into each other, and then double check it with light as well. The other thing that we could do is potentially look at neutrinos, which were released because they're able to escape before the light was able to escape. And so there's sort of two possible ways that you could probe the universe before the cosmic microwave background radiation was released: gravitational waves and neutrinos. And none of this is feasible today, but there is an observatory that's in the works. There's the LISA observatory that's coming out from the European Space Agency that's going to be in the next 10 years or so. And then one idea after that is an enhanced version of LISA called the Big Bang Explorer. And that would be like 12 gravitational wave satellites operating in a giant dodecahedron that would be able to detect those primordial gravitational waves. So we can't do it today, but in the next couple of decades, we should be able to do it. Akshay Bor. Hey Fraser, great show again. My question is, can you please explain in simple terms what is the halo of a galaxy? How big is the halo of the Milky Way and Andromeda galaxies? Surrounding the Milky Way is a halo. And the halo is actually three different things. There's the stellar halo, which is stars that are just outside of the disk of the Milky Way, and it's sort of roughly in a spherical shape. And so you've got globular clusters that are buzzing around the galaxy as well. And then you've got the gas halo. The gas halo is essentially hot gas that's produced by all of the star formation that's going on in the galaxy itself. It's sort of blasted out in all directions. And it's really hot, like 2.5 million degrees Celsius is in this gas, but it's very diffuse. So it's not like it's lighting everything on fire. And then surrounding that, you've got the dark matter halo. And they're very big. While, say, the Milky Way is about, say, 200,000 light years across, the halo around the Milky Way is about like 600,000 light years across. And in fact, astronomers recently did a big map of the halo around Andromeda, and they found that it extended out about 1.5 million light years away from the center of Andromeda. And if you kind of do the math and you take the dark matter halo, which is even bigger, of Andromeda, and you take the dark matter halo around the Milky Way, they're already starting to interact. And in fact, the halos between the Milky Way and Andromeda are getting very close to each other and will start interacting. Even though Andromeda is still 2.5 million light years away from us, the collision between our galaxies is already beginning. Lord, bite me, man. Fraser, we always hear about gas giants, but are there gas dwarfs? We don't have any gas dwarfs in the solar system, but they have been found. The smallest probable gas dwarf is or gas giant, gas planet, is a planet that is about 60% bigger than the Earth, but it has about the same mass of the Earth. So they were able to tell through its density that it is, and be able to figure out through its size that it's still a gas planet, even though it's not that big, only a little bigger than the Earth. And so you would imagine that these gas planets, even though they're smaller, they're still going to have the same kinds of constituents. They're going to have some kind of ammonia clouds, they're going to have water vapor clouds, and then they're going to have an interior that is mostly hydrogen and helium, and then some kind of rocky core in the middle, which is different from a terrestrial planet, which has like silicon and iron and nickel and various metals and stuff built in. Or an ice giant, right, which is going to have more ices with various heavier elements mixed in as well. And so, yeah, you can have ice giants, smaller ice dwarfs, gas giants, gas dwarfs, terrestrial planets, super terrestrial planets. We're still figuring out the tremendous variety of planets out there. All right. Thank you, everybody, for asking your questions this week. That was a lot of fun. I really enjoy this. As always, if a question pops in your brain, write them down. I'll gather them up, and I'll answer them here, and I'll see you next week. If you want a single, comprehensive resource for space news, you'll want to subscribe to my weekly email newsletter. Every Friday, I send out a magazine of space news with dozens of stories, pictures, brief highlights, and links so you can find out more. Go to universetoday.com/newsletter to sign up. It's totally free. And did you know that all of my videos are also available in a handy audio podcast format so that you can have the latest episodes as well as special bonus material like interviews with me show up on your audio device? Go to universetoday.com/audio or search for Universe Today on iTunes, Spotify, or wherever you get your podcasts. And I'll put a link in the show notes.